This is what we call a turbidite. Now let's have a look at an alternative model. This is what is an underwater mud flow. You know, when water is muddy, we say it's turbid water. It's muddy. Now, a turbidity current is an underwater mud flow. Now, in 1929, there was an earthquake in North America, and a piece of the continental shelf broke loose, and it roared under the ocean, breaking cables as it went, so they knew exactly how fast this mud was going. It was just going at a tremendous pace. After 3 hours and 3 minutes, it was 300 miles out to sea. That means that this mud was traveling at a speed under the water of 100 miles an hour. Now, imagine if you were a little creepy crawly or a fish swimming lazily at the bottom of the ocean, and a wall of mud as thick as this wall over here comes roaring towards you at 100 miles an hour. What would happen to you? You would just be fossilized in an instant, right? Now, this is what happened. Notice that we have a model over here. Imagine this is the surface of the Earth, largely extended. There's no mountain on scale that would be this high. And everything's underwater, and now there's an earthquake over here, and some mud is beginning to flow. Let's see what would happen. There it flows. Watch how it comes over the hills, into the valleys, over the top. And then it's going to settle down. And notice what it does. It's very interesting. It fills in the valleys while forming a layer over the hills. And this is soft mud, soft mud. Now we're going to put another layer on top of this while this is still soft mud. We're not going to stick around for a few million years waiting for this to turn into stone, okay? We're going to do it right now. While this is still mud, we'll have another earthquake in another place with a different color mud, and boom, there it goes. Watch how it comes around the corner, swirls clockwise. Do you see that? Goes down the hill, up the other side, and does the same thing. Now, do you think it's possible that you could whip some of the bottom mud into the top mud layer when it goes around the corner like that? Do you think it's possible? Possibly, yeah. Here's another one. Look, wham! Take some of the bottom layer, put it in the top, maybe. And then you settle down. And we're not going to wait a million years. We'll just let it settle. And then put another one on top. Notice the valleys are getting fuller and fuller and fuller. By the way, that's what it looks like at the bottom of the column, between the Cambrian and the Precambrian. That's what it looks like. Another layer. And another. And another. And now it's getting pretty flat. And now they're just rushing along nicely, one on top of the other. And then we have a closer look. What do you see? You see one layer on top of each other, and what are the contacts like? What's the contacts like? Flat. And especially on top, everything is flat. And can you see that here and there, for example, there's a little bit of mixing of the bottom layer into the top layer. Okay, if we go a little bit closer, notice what else we'll see. All right. If you look carefully, you will see that in this layer, from there to there, the coarser material, the heavier stuff, is at the bottom. Why? Because it's heavy and it settles out. And the finer material is at the top, because it's lighter. and it takes longer to settle. So this thing is graded coarse to fine, which is what happens in water. Now, if this layer had to form over millions of years with then a rain, and then a drought, and then a rain, and then a drought, and all these things happening, would the whole thing be jumbled up, or would it be graded coarse to fine? It would be jumbled up. If it's graded coarse to fine from the bottom to the top, what does that mean? That this layer formed how? Boom, catastrophically. All right? So if we go into nature and we have a look at them, here we are in the Swiss Alps, hundreds of these layers, one on top of the other. So it's just one after the other. Here we have some in Texas, and they've been lifted up. And you can drive to any of these areas in your country, you'll see beautiful examples. They were, of course, first flat, then they were lifted up later. These are all turbidites. How do we know? Because they're graded coarse to fine. Here are huge ones, big ones, showing tremendous activity. Here's another one. Notice the coarse material is at the bottom, then it gets finer, and then you have the fine mud over there. There are even some ripple marks saying that this happened underwater. And there's the next one, the coarse material to the fine material. Here's one in Australia. This one is in New Zealand, sorry. There you have the coarse material at the bottom. You'll see the pebbly, grainy stuff, the water lines, and then the finer stuff, and the next one starting on top. So how did they form? Slowly or quickly? They had to form just like that. These are mud layers that form just like that. Now, if you go to the Grand Canyon, you'll find a fascinating thing. From the bottom to the top, the whole canyon is graded coarse to fine. Wow. That means that the whole thing must have happened in a very short period of time. Now, the scientists will tell you, now, whoa, hold it a second. There are obvious regions in the geological column where we can say that this was a desert time period. How are you going to fit that into this watery situation? And they will cite areas like this in Zion National Park, for example. This layer, they claim, was a period of desert. And this over here is a desert dune. There's a problem here, because desert dunes never got to be this big, because they just cannot be that big in air. But underwater they can. And so they studied these in detail, and looking at the way in which it is laid down and how it is formed, they've come to the conclusion that after all, they were formed in water. So what happened? Let's assume you have a continent, and the mountains that are here today in the world didn't exist. Didn't exist. So it looked different, and you had huge inland seas and you had an ocean basin. And then something happened, and the whole continent was pushed under the sea. That means the sea would rush onto the land, and all the sediments in the sea would go onto the land. Then you would have the sediments of the ocean mixed with freshwater sediments here on the land. And then you do the reverse. You lift up the continents again, folding takes place, the mountain ranges form, and the new ocean basin forms. And the sediment that was in the ocean is now on top of the land, and you can see it in the mountain ranges and all over the place. And that's what it looks like. The sediment is on the land instead of in the ocean. Where should it be if the oceans have been around for hundreds of millions of years? Where should the sediment be? The bottom of the ocean. It's not there. It's on land. Well, that's very strange. Let's have a look at these layers. Here are two layers in the Grand Canyon. The one is called Coconino Sandstone. The other one is called the Hermit Shale. You can tell them nicely apart. They've got two different colors. And you can see some interesting structures. Boom, there's one. It's called the flame. Here's the one layer. There's the other layer. And here there's obvious mixing. Can you see that this one over here is as if it were whipped into the top layer? Can you see that? So something came rolling along and whipped up some of the bottom into the top and mixed them. Now, if this layer over here at the bottom were millions of years older than that layer, would that have happened, yes or no? Never. This is a geological nightmare, because this cannot be explained other than by catastrophism in water. Or could I depress a top layer into a bottom one, squelching it, not breaking it, going if the bottom layer weren't soft? Impossible. Could I fold mountain ranges like this or like this? Could I just take the layers and go like a bunch of layers of dough in a whatever donutty thing? Could I just go do that? No, unless the layers were soft. Now remember, science says each layer was the surface of the earth. Each layer constitutes millions of years turned into rock. How am I going to bend this without shattering it into millions of pieces? Impossible, unless the layers were soft.